Alright, so we continue again. Momentum transport, right? The last time we we are continuing from here from where we ended the other time, but let's just have some small revision, okay? So then when you see this again, rectangular system, coordinate system, you are thinking of what? X, Y, and Z, right? Then again, if you see X, sorry, that's rectangular coordinate system. Then again, if you see R, Z, and then an angle, then we are talking about what? Cylindrical coordinate system, right? So when you see R and two angles, right, the representation could be any way, but there's a general way. So we use R, this angle, and then this one. There's no rule though. To make it simple, let's just use this. So far as you see two angles, then we are talking about what? Spherical. Two angles and one radius. We're talking about spherical coordinate system. Okay, yeah. Here they've written x component here is that meaning that it's only the component of that equation that is expanded. You get to understand this one later, but like I'm just trying to give you some information ahead of time. Okay, then again, the constitutive equation meaning that the constant within the equation, so this is the constant, right? Okay, so this is shear stress, okay, and then this is velocity gradient. So you see gradient, whenever we hear gradient, you mean we are measuring something with respect to a particular direction. So you see velocity and respect to y direction, so velocity gradient, right? This constant here is what we call viscosity, to be particular kinematic viscosity. Okay, so this velocity gradient is what has been written here this way. It's still the same thing. Okay, so we say this is a constitutive equation because the constants within the equation are derived from experiment. Okay, depending on how the material responds to the factors or the spatial gradients when we are performing an experiment, right? So this is kinematic viscosity. Okay, this Bernoulli's equation you'll meet later. I'm just giving information, just some bits of information to get you prepared for what's ahead. Okay, so this one here is pressure, right? Pressure force. This is kinematic force. This is potential energy force, right? And this is energy performed on the system by the environment, right? And this is shaft work done by the system. Shaft work, what comes to mind? Like the shaft, right? But remember, you see, at times you have turbine, electricity are generated through turbines, right? Water flows and then it moves the turbine. So if we are considering the water to be at our system, right? So it means that the water has lost some momentum to the turbine, right? It has used some of its energy to turn the turbine. So shaft work. I'm just giving you this is energy on the system or work done on the system by its surrounding. Are we okay? Yeah. At times the equation can change, but they are the same. So you see, initially I said this is potential energy, right? So if I multiply it through by density, I'll end up getting this, right? Plus V squared on 2, right? And then I'll have rho G, this Z, you see, and then these ones come here. You see that then. So at times it can be arranged in different ways, but it doesn't change the fact that it's still the same equation. Are we okay? Yeah. So this is Bernoulli's equation. This one is the force, right? This kinetic energy, this potential energy, work done on the system by surrounding, and this shaft work. It's a form of work done by the system on the surrounding. Are we okay? Also, always remember to identify which is your system and which one is your environment in any particular scenario. Okay, so we continue. Definitions: steady state, right? State. Okay, steady state. When you hear steady, what comes to mind? Still, not moving, right? But let's go over this. So, steady state is saying that at a particular location in space, the quantity is the dependent quantity does not change at a function of time, right? So we see steady, right? Steady. It doesn't depend on time, right? So you see, if something does not depend on a particular quantity, it doesn't change with respect to it. So this is a way of writing this whole steady state mathematically, right? So if there were to be a change in time, so let's say if I have let's go back to some math, some differentiation. So if I have something like, let's say 2x, right, and I'm doing differentiation, let's say y is equal to 2x, and I'm finding the y, let me write it here, and I'm finding the y, the x, isn't it? So meaning I'm finding the derivative of y with respect to x, right? Right, yeah, so that's what it's saying. So if this y is equal to what, 2x, so you see it depends on x, right? It's having some x in whatever that is here in this equation for us to get our y, so it depends on x. So since it depends on x, if I do the y, if I'm finding the y dx, I'll get an answer, which in this particular case is 2, right? But in this case, they are saying it's not dependent on x. So if I have another equation, let's say y2, right, this y1, I'm finding y2, right, then let's say y2 is equal to 2, right, and I find the y2 dx, it will give me 0 because this equation here does not depend on y, does not depend on x. There's no x in this equation, so sorry, there's a mistake. It should actually be 0 here. So you see y is equal to 2. There's no x in this particular equation, right? So if I find the, so if I'm finding the y2 dx, right, I'm just putting this one here to signify this, right? If I find the y2 dx, it should give me 0, right? Even if I were to have something like this, let's say y3, let me write it small, y3 is equal to, let's say 2a, and I'm trying to find the y3 dx, this is 3, it will still give me 0 because this particular equation here has no x in it, right? Simple differentiation rules, right? But if I were to do something like, let's say the y3 dA, that's where to give me what, 2, right? So they are saying that in steady state, at a particular position in time, the dependent variable, which is this, the quantity that we talk about. So you see, when we started, I said that we are building the basic concept, so try to remember everything. So this is the conserved quantity here, which could be mass, momentum, right, chemical species, or energy. So this conserved quantity here is not a function of time, right? So that's why when you find the derivative with respect to time is 0, right? It doesn't depend on time. That's what it says here, right? Next one. So yeah, so what do you think this one happens? So you see the same derived quantity, right? The reason why we are seeing this particular curl d here is saying that we are doing partial derivative, right? So we are not doing it only in one direction. We are not doing it in only one direction. So we are doing the alpha, the t in x, y, z. So that's why we have this slanted d. It's actually delta, right? Not 4d like the normal differentiation like this one that we know, right? Not this. So you see, because we are doing it in 3 different directions, we are doing the partial derivative, right? The same thing here, but because we are doing it in only one direction, or we have ordinary derivative, right, we are doing it with respect to only one, right? It could be any of these ones. 4d is still 0, right? It means that a is constant, or whatever the function that it is, it doesn't depend on x, y, and z. Are we okay? And then we have uniform, right? Uniform mean that in every direction. So you see steady state, steady state, steady time, right? Not the function of time, as we saw here. Steady state, not a function of time. So the derivative with respect to time is there, right? So now we are not doing with respect to time, we are doing with respect to what do you call it, position, right? So you're saying at a particular instant in time, okay, the dependent variable is not a function of position. So you see, uniform, we are checking how it depends on position, right? Steady, we are talking about how it depends on time. So okay, so you see the same idea here, partial derivative, right? Because we are doing it in different directions, now we are talking about just one of those three possible directions, right? We are talking about it with respect to position. So you see, this x, this is y, this is z, right? When we are talking about a particular one among all the possible uh, among all the possible things that we could compare the conserved quantity, we are comparing with x in this position here. X, you see, this is y here, this is z here. So you see, we are talking about position, uniform position, all directions, x, y, z, 0. Okay, so you see, it's not a function of the position at any particular time. Later you see diagram that explain this. So you see the other time I drew something like this, and then we had something like this, right? Yeah. Later you get to understand how all this diagram connect with all this. So then again, these are basic concepts, the underlying concept, the fundamental concept. When you understand these ones, moving on forward, it won't be that much difficult for you. Okay. Yeah. And here we talk about gradient, right? So when we say gradient, we are talking about respect to position, right? Variation of physical quantity with respect to position, we say gradient. So you see, there was a particular equation that was something like this, where I said, let me write it. That was something like this, right? Mm, that was something like this, and we had a negative and this, and then we had the VZ and something like DX or something, right? So you remember that I said, let me write, this is shear, I said it was stress, this is kinematic viscosity, this is velocity, right? And this is x dx, right? So this is what I said was the gradient, right? But this is a particular gradient, this velocity gradient. In another case, you could see something like the dt dx. This one could be anything, this one could be anything, depending on the quantity we are talking about. Okay, so this is velocity, right? This is temperature, right? So the moment we get a particular quantity with respect to a position, this x here could be, let's say, dy or dz, we are seeing this whole thing here is gradient, right? So but we have specific names. Okay, yeah. So the gradient of a quantity must be zero for uniform condition to exist with respect to that particular quantity. Okay, yeah. So the gradient must be zero for uniform condition to exist. So okay, so uniform condition, then again, uniform condition, right? Respect to x, respect to y, respect to z, 0. So they are saying that for the uniform condition, which came before this, for it to be obeyed, the gradient, which is this, something like this one or something like this, should be 0. Where here is a conserved quantity, here is a particular direction in the coordinate system. Okay, depending on the coordinate system. Okay, and then equilibrium. Equilibrium is a system said to be in equilibrium when both steady state and uniform conditions are met. Okay, so steady state, how do you write it mathematically? Steady state, right? We are talking about time, steady time, right? Okay, not study, steady. Okay, stady, right? This means time, right? So steady state means that when we do something like this, a particular quantity a with respect to time, 0, right? Right? Or it could be partial, something like this, particular quantity with respect to time, 0, right? So this is what we call steady state. There's one way of writing it. So for it, a system to be in equilibrium, this one, steady state, which is this one, and the uniform conditions, right? Uniform condition is where we have uniform, where we are talking about position or gradient, right? So it could be something like this: quantity with respect to x, right? Quantity with respect to y, depending on the coordinate system. Okay, quantity with respect to z. When all these are 0, then we say that what do you call it? Uniform conditions are exist. But when these two exist together, when this is confirmed, when this is equal to 0, confirmed, and these all equal to 0 for a particular coordinate system. So you see x, y, z, which will mean what? X, y, z will mean rectangular coordinate system. So it could be something like this: the particular quantity, the r, right? Particular quantity, the z, right? Particular quantity, the what again? The theta, right? So when you see this, a distance and an angle, what are you talking about? Cylindrical coordinate system. So okay, the equations could change depending on the system that we are talking about. Okay, yeah. So you see, when steady state condition, time, right, and equilibrium conditions, position, when both of these are true, then we see that the system is in equilibrium. Okay, when they are met, when steady state and uniform conditions are met simultaneously, we say the system is in equilibrium. Are we okay? Yeah. Now we meet something, we see flux, right?